Okay, I'm gonna tell you something called Emirp. Okay, I'm gonna tell you something Emirp. Now, I want you to take Emirp and reverse the way you spell it. You get the word prime. Prime. You reverse to get prime. Now, this isn't just like a fun wording game, like a fun fact about words. Oh, that it's quite cool. If you take prime, you reverse it, you get Emirp. That's a fun fact. No, that's not a fun fact. That's not a fun fact because Emirp is actually a thing. Now, Emirp is a number, and Emirp is a prime number that when you reverse, like how you reverse the word here, ironically, but like when you reverse it, you will still get a prime number. Let me give you an example. 13 is an Emirp. Why? If you reverse this number, you get 31. And both are prime. I will give examples of something that are not Emirp. Now, firstly, an Emirp must be prime. And secondly, when you flip it over, it must still be prime. So, let me give you an example. 19. You may say, oh, 19 is an Emirp. No. 19 is prime, but when you flip it over, you get 91. And 91 is actually 13 times 7. So, it is not an Emirp. That means when you flip it over, it must still be a prime. So, some examples are 13, 31, 17, 71, 37, 73. Alright, there's actually a lot more. I want you guys to write down in the comments as many as you can come up with. Alright? Okay, now let's move on. Let's talk about something else. Okay, I'm going to talk about Goldbach's conjecture. Goldbach. I don't know whether it's Goldbach or Goldbach. Okay, I don't really care about the names. Goldbach. I don't know. Okay, but we shouldn't be talking about this. And basically, this theory states that any number, actually any even number, except for 2, is the sum, of 2 prime numbers. What do I mean? Now, I'm not gonna give you an example of this because I think it's dumb. Okay? But, essentially, I want you to think about it. I want you to take any even number except for 2. Any even number you hit. I can guarantee you with Goldbach's conjecture, proven, that it is definitely the sum of 2 other prime numbers. I'm gonna give you one simple example only. I came up with a random number, 38. It's a random even number. It can go as big as possible, but let's just use 38. Oh, sorry, no, sorry. It's wrong. One is not prime, it's accident. 38. Let me think. 38. It's actually, let me think. 31 plus 7. See? So it's proven. Any even number except for the number 2, any even number, is definitely the sum of 2 prime numbers. You can try it out yourself, alright? Okay. Now, another fun fact is that 2 is the only even prime. And if you think about it, you probably know why. Now, actually, most even numbers, they are all prime, except for the number 2. All even numbers, in fact, except 2, they are all prime. Sorry. They're all composite. Sorry. All even numbers, except for 2, they're all composite. Why? Because even numbers are defined that they can be divisible by 2. Right? That's literally what we mean by even numbers. If it's an even number, it can be divided by 2. Right? That's the basic definition of what an even number is. Okay? So, if it's an even number, you can divide 2. But that literally just means that it will be composite, right? So, that is literally why every even number will be composite. But 2 is the only even number that's prime. Because 2 is an even number. which is what 2 times 1. But it perfectly fits the rule of a prime number, right? And there's no other way, because 2 is so small that itself is basically just the rule of even numbers, which can be divided by 2. So that's why 2 is the only even prime. Okay, now, I'll give you another fun fact. The fundamental theorem of arithmetic. Now, the fundamental theorem of arithmetic, okay, it states that any composite number, right, is definitely made up of prime factors, which basically means that any composite number, you can just multiply this, multiply that, multiply this, multiply that, and these factors that you multiply by, they're all prime factors. What do I mean? Now, if you have any composite number in the world, right, there is definitely a way. Okay, I'm just gonna give you an example. Number 28 is composite, right? I can definitely make it such that it is a product of prime factors. There we have it. 2 times 4 times 7 is 28, agree? So the fundamental theorem of arithmetic states that any composite number is will basically can be factorized in such a way that all the numbers are prime. Alright, and we'll learn more about this in prime factorization, which is another video, about how you can factorize you can do prime factorization, how to do prime factorization. Okay, but essentially, the fundamental theorem of arithmetic states that as long as it's a composite number, alright, in one way or another, you can make it such that the entire number is factorized this times this times this times this, and all these factors that are prime. That's literally the meaning of, that's literally what the fundamental theorem of arithmetic states. And lastly, do you know there's actually a method to test for primality? Okay, so now the method states, it's actually super simple. The method states that if a number cannot divide all the primes less than its square root, it is prime. Now what does this mean? Okay, so for example, if I have n, I want to test for its primality. All I need to do is to take n and square root it. And I'll just get this random number. Let's say x. Now, essentially, I just need to take n and go and divide all the numbers lesser than x, all the primes lesser than x. So let's say x is 36. I'm going to divide by all the primes lesser than 36. 31, 29, 23. Alright? And let's try it out. Can n divide 31? Let's say n cannot divide 31. Can n divide 29? Cannot divide 29. Cannot divide 23, blah blah blah. Okay, and I try all the way until we reach n divide by 2. And also n can divide 2. So I can straight away conclude n is prime. But how do I know that? Okay, it's actually super simple. Alright, now this method is used so that life is not that tedious for you. Because you know whenever you want to test primality, you've got to take the number and you're going to start dividing it. Alright, can it be divided by this? Can it be divided by this? Can it be divided by this? But it will take forever. So this method is going to make it easier for you because you don't have to try everything. But here is something that is not that good about this, is that although it will help you lessen the tediousness. It won't be that difficult. But if you're dealing with a big number, this method will still not be able to work that well, because it is still gonna be to some extent tedious if you're gonna work with big numbers. If you're working with small numbers, any test for probability works. But this test for probability and any other test, they work for small numbers, but when you reach big numbers, nothing really works. So that's why it's harder to test for probability with big numbers. So I wouldn't say that this is like the perfect alternative to your classic testing for probability, because this one also doesn't really work with big numbers. So well, it isn't that good, but there's nothing else we can do, right? Okay, so now let us see why this works. Why do we just need to divide all the primes less than the square root? Why cannot we, alright, let's say the square root of n is like 27, right? But n is 27 times 27, okay, which is 729. So, if I'm asked, determine whether 729 is prime. A lot of you may start saying, oh, I have to divide 2, divide 3, divide 4, divide 5. All the way until divide 729. Actually, you don't have to do that. You just need to divide the primes that are less than its square root. Why? Why cannot I divide the primes above its square root? Why can't I divide 29? Why can't I divide 21? We need to check a full proof, right? Okay, now the reason that you don't need to do that, I'll explain. Okay. So this method is actually better than your classic method of dividing by everything, because there will be way lesser things to divide. But as I said, still, if you're going to be dealing with big numbers, this method still won't be flawless. There will still be flaws in it. Okay, but at least it's better than your classic methods. Okay, so now I'll explain why. You don't need to divide by everything, you just need to follow this rule. Okay, let us go through something super simple first. Can we all agree on this? I think it's like a no-brainer, right? Right? Agree? Okay, now, here's the thing. Hey, is it possible that I have a number which is greater than the square root of x times another number that is greater than the square root of x, and yet I get x? Is this possible? Is this statement even possible? No, this is not possible. Why? Okay, think about it. The square root of x times the square root of x, you get x. This statement is telling me, hey, if I have a number that is greater than the square root of x, and times another number is greater than the square root of x, I'm going to get x. How is this even possible? This is definitely true, no matter what the value of x is. But here's the thing. If this is greater than the square root of x, the value of x will increase. And if this is also greater than the square root of x, the value of x will doubly increase. There is no way this equation can make sense in any world. I don't care what this value is. I don't care what this value is, but this doesn't make sense. Because this times this will give us this e. But if you're going to add in this more than, this stands for more than the square root of x times more than the square root of x, you get x. This is not possible, right? Agree? So we can agree on that. Okay, now, this makes sense. But if you're going to increase, you're going to take something greater than the square root of x. You are going to take something greater than the square root of x and expect to get x. That's not going to be possible. Because if this is, okay, these two statements are contradictory. Agree? So only one of them can be true. They can't be true at the same time. And we know that this is, of course, mathematically true. So this is just completely wrong. Okay. Now that we know this, let me ask you a question. How about this? Is this true? Think about it. It is true. Why? Because you can see that it's not true exactly, but it's possible, right? It has a possibility of being true. Because think about it. This is smaller than the regular, which will decrease the value of x. This will increase the value of x. This one will increase. This one will decrease. So this will create sort of like a balance, and it's possible for this, right? I'm going to give a super simple example. Say x was 4. I'm sorry, say x was 16. Make sense? But if I have this, I don't care what number it is. This can't make sense, right? Be bigger than the square of 16, and we know that's 4. Let's just say 5. Let's just say 5. That also doesn't make sense. But, however, if I were to do something like this, it's possible. Something that's greater than the square of 16. Square of 16 is 4. Something greater. Let me think. 8 is greater than 4. Something smaller. 2 is smaller. Makes sense, right? Because this increase, this decrease balances out. So, if you look back here, in fact, we just need to make sure that all the values below its square root, all the primes below its square root, cannot be divided. And we know that this entire thing cannot be divided, so it's prime. Okay? Now, if you think about it, we have proven that this is possible. Okay, this is possible. But this is impossible. Okay, it's no way possible. Okay. So, now, if we are going to just check, we're just going to fill in the blanks. Okay. This means less than the square of x. Now, if we know that all the primes below the square of x are basically cannot be divided up, right? The number cannot divide all the stuff below the square of x. That means that there will be no factor like this, right? I'm trying to test for the primality of x. I square root it, I square root x, I get this. So all I need to do now is I'm just gonna look at all the primes less than this value. And I see nothing. So this is non-existent now. I see nothing, right? Now, if this is non-existent, the only thing that can be existent at this point will be this. Agree? So now, two factors. The only possibility now, because there are two variations. Variation number 1 is like this. Variation number 2 is like this. We have already eliminated this variation, which means we are only left with this variation, which means that in both the blanks, we must fill it in with this, which will be this entire thing. But we have already proven it to be wrong. Agree? So, I'm going to explain this one more time so that you can hear this clearly. We know this is possible, but this is impossible, right? For any value. So, actually, if you think about it, we can just be flexible. We don't need to check this. Some people would say, we need to be smart. We need to check things greater than the square of x and also the primes smaller than the square of x. But in reality, nope, we don't have to check both. We just need to check the one smaller than the square root of x. Okay, we just need to check this. Because once we have determined that, hey, nothing works because to check the square root, to check for primality, agree that to check for primality, prime means cannot divide by anything except one and itself lah. Prime means cannot divide by anything. That's the ideology we'll have. Prime means cannot divide by anything. So some people like to say I check cannot divide by the things smaller than the square of x, and also cannot divide by things greater than the square of x. But as I said, we only need to check this. We don't need to check this. So let's check this. We are gonna check the stuff that is gonna be smaller than the square root of x. We finished checking, and we've checked that everything smaller than the square of x cannot divide by anything. Okay, so we know that nothing can be here. There's only one thing left. This left, agreed. So since we've eliminated this option, since we've finished checking and we've seen nothing can divide, right? Bye bye. We are gonna eliminate this. Now it will only, because now we have checked everything less than the square of x, and we agree that there's no factors as such except one. No other factors as such. Which means that the only factor you could possibly get will be the things that are more than the square root of x. So, under the condition of something times something equals x, there are two things we can put here. We can put more than the square of x or less than the square of x. Okay, but here's the problem. We have already proven that by dividing, that this option is gone. There's nothing less than the square of x. So it only leaves us with this thing. Means I can throw this in here, throw this in here. If you look at this, you realize that from the start, we have already agreed that this is impossible. So you can clearly see that we don't need to eliminate both options. We have two options here. Greater than square root of x, smaller than square root of x. We just need to check that there are no factors in this category. Because once we finish checking that there are no factors in this category, we know that the only category left on the table is this category. And some people will tell me we have to check this, but we don't have to check this, because if there is only this left, we will know that there's no way we can formulate a proper equation, a proper factor multiple kind of board. You will always get this type of case, because that's the only option we have. And we know that this whole thing is theoretically wrong. So that's the test for primality. Right, thank you very much. Hope you enjoyed this video. Hope you learned some things about primes, some things that you didn't realize. Okay, and if you enjoyed this video, please consider liking and subscribing. Alright, drop any questions you have in the comments. Share this with anyone who's interested. Alright, who's always like, oh, I really want to learn more about primes. Alright, but that's it, and goodbye.